So we just described how to analyze and look at numerical data in terms of summary statistics. Right? We have measures of spread, measures of central tendency, and measures of location. Well, how do we visualize a numerical variable? We have several techniques we can use, and these are just some of them. One common technique is to use what's called a stem and leaf plot. It provides a way of listing our data. The idea is that the numbers to the left of this vertical bar are called the stems, and the digits to the right are called leaves. All the stems that begin with the same digit and the corresponding leaves, written next to each other, allow us to reconstruct any particular observation of the data set. A stem and leaf plot, it's really best when you have a small data set, a relatively small data set, say 50 observations or 75 or 10. It breaks down and it becomes intractable when you have a very large data set. Right? We have other techniques for that. But here's a stem and leaf plot for a pretty small data set. These are the stems, and then we have the vertical bar, and these are the leaves. And you can see here that we can reconstruct every single observation of the data set. In this particular data set, it's based on years, okay? It's the age of a bunch of people. So here we have 54, okay? That is the minimum value of the data set. 79 is the largest value in the data set, right? We can reconstruct every single actual numerical value in this distribution. You can also see that it has a kind of skew, right? There's an outlier. 54 is much lower than the rest of the values on the distribution. The problem with a stem and leaf plot is that it breaks down with relatively small data sets even. Like if you have a data set of 100 people, a stem and leaf plot can be kind of difficult to use, and you may not want to reconstruct all the different observations. So what do you do when you have a larger data set? What happens if you have a data set of like 50,000 or 1 million people? Well, an alternative is to create a histogram. The idea is that it shows the distribution of a numerical variable, right? But it uses bins. It bins the different sets of observations. Right? Specifically, a histogram shows how many data points or observations are within a given interval. So each bar covers an interval or bin with the height of each bar equal to the number of observations in that interval. So here we can see that most of the observations are kind of around 60 or so. There are very few observations around 50 or 40, relatively few observations up around 80. So histogram gives us an idea of the distribution. And again, it's particularly useful when we have large data sets. A related technique is something called a density plot. Intuitively, a density plot is like a histogram, but with really small bins, right? So small that they're kind of smoothed out. The height of a density plot, it can give us an idea of where the observations or data points are concentrated. You also see here that so that the density plot is not misleading us, right? So that we are aware of where the data points actually lie, the statistical software gives us what's called a rug of jitter data points. Jitter just randomly scatters the data points so that they're not directly overlapping each other. And this gives us an idea of where most of the data lie. So you can see in that tail, there aren't really very many data points. Most of the data kind of cluster around that heap, that sort of mound part of the distribution. Density plots are quite useful as an alternative to histograms. So here's a density plot of life expectancy. Okay? We also have box plots. Right? A box plot is another way of looking at a distribution of data. We have a dot in the middle, that's the median or 50th percentile. Then we have this box. That box is bounded by the first quartile and the third quartile, or the 25th percentile and the 75th percentile. Then we have these two whiskers. Sometimes a box plot is called a box and whisker plot. That's because of these two whiskers. Right? The whiskers are defined by the minimum observation that is not an outlier and the maximum observation that is not an outlier. The thing about a box plot is that the definition of outlier will vary. Different statistical software packages will define what an outlier is in different ways. Conceptually, the idea, and so you should always check to see how they define or how an author defines what an outlier is. But the basic idea remains the same. You have a box in the middle, which is almost always defined, as far as I can tell, by a first quartile and a third quartile. And then you have these two whiskers. And at any point beyond those two whiskers is considered an outlier. So here we have an outlier way off to the side. A related concept is skewness when we look at the distribution of a numerical variable? Look and consider the skew. We can talk about distributions being skewed left, skewed right, or being symmetric. A symmetric distribution is such that the mean, the median, and the mode, they're all the same. Right? But when you have some kind of skew, right, when you have a tail to the distribution, right, it's going to pull that mean, right, relative to the median. Okay? In general, the mean will be pulled to that direction of the tail. Right? Consider the case of income in the United States. Income is a skewed distribution. So if you look at the average compared to the median income, right, because there's sort of that skew, you have relatively few people making a lot of money, that mean as a measure of central tendency relative to the median is going to be pulled towards those very high incomes. So it's always important to consider how our distribution is shaped and the different ways that skew can manifest itself, and also its relationship to the median relative to the mean. And with that, we've covered the basic ideas of visualizing numerical data.